All right, here's our last video for 3-5 related rates for the essentials of calculus. So we're looking at a problem where gravel is falling on a conical pile at a rate of 10 feet cubed per minute. At all times, the radius of the cone is twice the height of the cone. Find the rate of change of the height of the pile when the radius of the pile is 6 feet. So let's start by writing out what we know, okay? Well, we know, let's just start going through the problem and underlining or highlighting. I'm going to highlight, but I don't believe you can highlight on the AP test, so you would underline or circle. Okay, so gravel's falling on the conical pile at a rate of 10 feet cubed per minute. So that feet cubed per minute tells us that this is a volume, right? Because that would be cubes per minute. So that means the volume, the rate of change of the volume with respect to time is 10. Okay, so dV dt is 10. All right, now the cone, the radius, there we go, there's the next thing. The radius of the cone is twice the height of the cone. Okay, so that's another thing we know. So we know that the radius is always equal to 2 times the height. So I can keep that. And then find the rate of change of the pile when the radius of the pile is 6. So that's another one, when the radius of the pile is 6. So when radius equals 6, I want to find, and then I could come here and say, okay, what am I looking for? There's another color. Okay, what am I looking for? Well, I'm finding the height of the pile, right? That's what I want. So I'm going to write over here, I'm going to say, oh, not in that one. Nope, not in the, not in the highlighter. Okay, we're going to find, or not, let's see if it's going to write. Find, oh man, we'll just do it over here. Find the change of the height, so dH, with respect to time. Okay, so we're trying to find the change in the height as time moves on. Okay, so let's take a look at how that's going to look. Well, how do we write an equation for the volume of a cone? Now, you can look back at your little cheat sheet we have there. The volume of a cone equals 1/3 pi times the radius squared times the height. Okay, so this is our function, right? Now we want to find how fast this function is changing, because the derivative is how fast something is changing, right? So we want to figure out how fast is the volume changing as the radius and the height are changing. Okay, that's why it's a related rates, because the volume changing, the rate of change in the volume, is related to the rate of change of the radius and the height. Well, the very first thing that we know is that we know that we have 3 variables here. See, we have v, and we have r squared, and we have h. And we want to get as few variables as possible because it's less we have to differentiate. In fact, if we differentiated this right now, we'd have to use the product rule. No, we don't want to use that, okay? So we do know that the radius equals 2 times the height. So we could just substitute that in, right? If r always equals 2h, instead of r squared, we could just put 2h squared in there, right? Okay, so let's do that. So we're going to just substitute in volume equals 1/3. Oh, there's that spot again. It doesn't like to write. All right, we'll just try it down here then. So volume equals 1/3 pi times 2h squared times h. Okay, so that means we have volume equals 1/3 pi times 4h cubed. Okay, now we only have one variable to differentiate on the one side and one variable on the other side. That's so much easier, okay? So now we need to find how much this is changing. That's a derivative, right? So we're going to say how much is the volume changing, dV dt. when this other stuff is changing as well? Well, let's see, we can rewrite that as 4/3 pi. That's not changing. That's a constant, right? Okay, but our variable h is changing. So we have 3h squared. But remember, we're differentiating with respect to time. Time is our independent variable, and h is a function of time. So it's a function inside of a function. So we just took the derivative of the outside function, but we need to tack on that dh dt to account for that inside function, the derivative of the inside function, okay? So we are trying to find this, right? Ooh, that does not look pretty, but oh well. How about a different color? We are trying to find, we want to find this, right? So let's plug in everything that we know. Do we know dv dt? Yes, we do know. If we come back up here, dv dt is changing at 10, cubic feet per second? Per minute. Okay, so dv dt is 10. Then we have 4/3 pi times 3, and then h squared. What is h squared? We don't know h squared right away, do we? So we have to do a little bit of algebra. Okay, well, what we do know is that the radius equals 6. Right? That's one thing that we've been given. We want to find this rate when the radius equals 6. Well, if the radius equals 2h and the radius equals 6, then our height has to equal 3. So we can come back in here and we can plug that back in. We can say 10 equals. Now I'm going to multiply this 4/3 by the 3 so that I can have just fewer numbers right now. So that would be 4, right? I just multiplied this 4/3 by the 3. Okay, 4 pi, and then h squared, which is 3 squared, dh dt. Okay, so we're there now. And now we just start solving stuff, right? So we have 10 equals 9 times 4, which is 36 pi dh dt. And again, we're trying to find dh dt, so we want to divide both sides by 36 pi. And we come up with dh dt equals 10 over 36 pi, which simplifies into 5 over 18 pi feet per minute. So that's how fast, that would be how fast the height is changing with respect to time for those very specific conditions that we were given. So I hope that you have a little bit better understanding of related rates. This one is kind of a big topic. This one definitely is like application. And so if it's still fuzzy, that's okay. We will work lots in class and hopefully you can get them.